All right, welcome back. So as promised in the last video, now we're going to look at examples where there's actually a transfer of energy between mechanical and internal energy. So we're kind of going to go from here to there. Okay, so this is just a good kind of taking a step back and summarizing what we've learned so far in this class. We started with just looking at changes in thermal and bond energy. Thermal energy when there's a change of temperature, bond when there's a phase change or chemical reaction. And then you were introduced to the relationships between the energies and their indicators. Then we've been talking about now mechanical energy. So we're introduced to kinetic energy. It says translational here because you're also going to see another type of energy. We're not going to go into too many details with it in 7a, but there's also rotational kinetic energy that you'll see. I didn't talk about it directly, but you will be introduced to it in DL. And here's the relationship between kinetic energy and its indicator, which is speed. Then we looked at two types of potential energies, gravitational and spring mass. Both of them have to do with the physical position of the object. Gravitational potential energy has to do with height away from the Earth or towards the Earth, and the spring mass has to do with distance relative to its equilibrium position. All right. So unfortunately, we're not in live lecture, but if we were, I would show you this kind of fun demonstration with two types of balls. One is called the happy ball and one is a sad ball. And why is the happy ball happy? Because it bounces back up. So you throw it down, hits the ground and bounces like most balls do. But there's also this sad ball that I would have that would actually look identical, but when you drop the sad ball, it doesn't bounce at all. It just plots on the ground and that's it. So let's think about what exactly is the difference between these two balls? Or in other words, how is the energy transferred differently when the happy ball hits the ground versus the sad ball? So let's look at this, focus on this interval the two balls are falling down, they're about to hit the floor. Until they hit the floor, they're identical, they have the same mass, and as we'll see shortly, actually mass doesn't matter. But right before, if you drop them from the same height, they should have the same speed right before they hit the ground, except one ball bounces and one doesn't. So the final interval we want to look at is when the ball is in contact with the floor. Both of them will have a time when the speed is 0. For a sad ball, it's gonna stop and stay stationary. So it's gonna be its final moment, where the happy ball does bounce back, but at some moment as it's turning around, its speed has to go to 0. So let's look at the energy interaction diagrams for both situations. So what's happening with the happy ball? Well, in the happy ball, okay, the kinetic energy goes down from right before it hits the ground. It has kinetic energy, and when it's turning around, as it's touching the floor, its kinetic energy is 0. But then how is that energy being transferred? What's allowing it to bounce it back up and gain mechanical energy again is, in this case, because the ball is elastic, it's able to compress. So compressing, you can, the spring mass system that we looked at, that's a very specific system with a spring and a mass, but any type of elastic object can be described with the same type of model, as long as the distance from equilibrium is not too large. So you could think about the ball's sort of equilibrium as when it's just relaxed, and as it hits the ground, it compresses. So there's this distance away from equilibrium, which results in the increase of this potential. And let's just keep the vocabulary of spring, really, it's kind of the elastic potential energy. So it gets converted to that, and then later as it bounces back up, as we'll see in the next slide, that goes to kinetic energy. Now, what happens with the sad ball? The sad ball, on the other hand, just stops. So if it stops, we know that its kinetic energy goes down, and then it doesn't really get converted to any kind of mechanical energy. It stays stationary. So its interval is over. Nothing else happens after that. So we know that all of our mechanical energy gets lost. Where does it go? Well, it has to leave. So that means that there was some work that the object did on its environment, or the work left the system. So this is the equation here. So here we can kind of almost model it as a closed system, where this is 0, where here all of it went to work. Now, what is this work? Work always has to do with some force, and that force comes from an interaction. So what's the force? Well, the force is the force of the ground onto the ball. So if we were to, let's say, include the ground or the floor in our physical system, then it would become closed. If we take everything that our object is interacting with and put it inside the physical system, that means that the system is closed. So then if one type of energy is going down, what's that other energy that has to go up then? So there's kind of two ways basically of depicting this energy interaction diagram. Make it open and say energy just left. Or if you really want to analyze what exactly is that energy, kind of like when we looked at our baseball player, instead of just saying he does work on the ball, we thought about, well, if we included him in our physical system, then he must be losing energy. And he was losing his chemical energy by doing work. So here, if one energy goes down, that means another energy had to go up. And what exactly is that energy? That energy is thermal energy. So it's this impact of the ball on the ground. They rub together. It's kind of like effect of friction, which will always give us thermal energy. But because it's complicated to think about the details of that thermal energy, we often will just model as an open system with work going out. But again, here is an example of purely transfer of mechanical energies, where here we're losing energy, but we know that energy cannot be created or destroyed. So where is that energy going? It's going to thermal type of energies. Okay. So let's now continue thinking about our balls. Well, the sad ball is done. It's just stopped on the ground. What's happening to the happy ball after it leaps back in the air? So here, let's look at the interval. Let's now make the initial time of our interval the final from the previous slide, when it's in contact with the floor, turning around. And then the final is, where it's no longer touching the floor and leaping back up in the air. So now we have all that potential energy that it has due to its compressed elasticity of that ball. Now it goes back to equilibrium as it returns to equilibrium, as it's leaping back up in the air, and all that then potential energy gets transferred back to that kinetic energy, allowing the ball to leap back up in the air. Thermal energy is not able to do that. So things cannot spontaneously cool down and convert to kinetic energy. So this is kind of although from everyday experience, we know that for a fact, but it's subtle from a conservation of energy point of view, because conservation energy, there's nothing about it right now that tells us that things can't just cool down. So thermal energy goes up, kinetic energy goes, or thermal energy goes down, kinetic energy goes up. Still abides conservation of energy, but it clearly never happens. So when we get to entropy, towards the end of the class, you'll understand why that is. So we just don't have the tools yet to explain why that actually doesn't happen. All right. So what I want you to think about here for this question is, how can we know for sure that the happy ball Earth system is truly a closed system as it bounces back? So the question is, did it lose any energy to thermal energies, or is it closed in the sense that it's only mechanical energy that's being transferred. It's not, the interaction with the floor is not relevant. So it's a closed system. We know how can we know that? Because it does not interact with anything else. The ball bounced back up. Is that what tells us it's a closed system? Only if the maximum height after the ball bounces is the same as the initial height. Only if the speed when it bounces back is smaller than the speed before the impact, or only if the speed when it bounced back up is greater than the speed before the impact. So think about this, think about it in terms of conservation of energy. All right, so let's see. Okay, so let's actually look at all the choices. It's a closed system since it doesn't interact with anything else. Well, that's not true. It does interact with the floor. It does hit the floor, and it's that floor that compresses, allows the ball to compress and bounce back up. So it does interact with something else, which kind of already should tell you it cannot be a perfectly closed system. The ball bounces back, yes, but that's not what makes it a closed system. What would make the ball in the earth a closed system is if its total energy is conserved. So how could we know that the total energy is conserved if the energy it started with, which is just that potential gravitational energy before you dropped it, was the same energy that you got back when it bounced back up. So if the maximum height after the ball bounces is the same as the initial, then we can conclude it was a closed system. And then here, if the speed is smaller, that means some of that energy was transferred to thermal energy of the with the floor. So you can get a ball that's super bouncy, but you can never, first of all, you can never do it so it goes higher than its initial height if you just drop it. But most likely you will never have a perfectly closed system, because of course the ball still interacts with the floor, and there's still going to be some, even if it's small, transfer of thermal energy with the floor. So you can never really have a perfectly closed system. But in physics we often make approximations. So when something is very close, when friction can be almost neglected, then we tend to neglect it. When other things have a greater effect than something else, then we often, to simplify our model, will neglect the things that have a smaller effect. But if you were in lecture and I showed you this, it would be very obvious, even with a ball that bounced, that it does not come even close to the original height I dropped it from. So in that, at least the ball I have there was definitely loss of energy to thermal energy with the floor. Okay, so here's a more realistic situation as the happy ball bounces back up. So imagine I release it at 1 meter, and you can measure how high does it come back, and it turns out, let's say it comes back to 0.8 meters. So how would you depict this interval? Well, there's no speed difference because we're just looking at the moment you release it, initial speed is 0, and then it comes back up to its maximum value. Maximum height, it means it's right before it starts falling again. So it's turning around, so the speed is 0. So we only, in this interval, although again, the ball is moving in between, all you care about is what are the indicators at the beginning, at the end. So in this interval, there's no change in kinetic energy. We start with a higher value than we end with. That means that, we go from 1 meter to 0.8. So gravitational potential energy goes down. What does that tell us? It's not a closed system, it's an open system. So that means that work was done on the system, work left the system. Where did it come from? It came from that interaction or the force by the floor on the ball. So there's still some energy, that mechanical energy, that was lost to thermal energy due to the interaction with the floor. All right, so for the sad ball, all of that energy was lost immediately. Here, some of the mechanical energy got retained, but some of it still got lost. All right, so here's another kind of fun example. So what I suggest you do is pause the video and type in this link and watch the video. So what this shows is footage from the Apollo 15 mission to the moon. And one of the astronauts there takes a hammer and a feather and drops them. And what you see actually, when the hammer and the feather drop, they land at the same time. And you know, from everyday experience, that seems really counterintuitive, because you know, if you did that on Earth, the hammer would most likely land first. So let's think about why that is. So the hammer and the feather fall to the ground at the same time on the moon compared to the Earth because. So watch the video first, look at the choices and think about it again. Always keep conservation of energy in the background. All right, so let's take a look. So the key here is because on Earth, on the moon, there's no air. There's no atmosphere, there's no air, so there's no air friction. So why does that matter? Well, if we look, so this is kind of a pretty involved question. So if you work out your conservation energy on Earth, we have, as the feather or the hammer drops, we have it increasing in kinetic energy. So its final kinetic energy before it hits the surface is 1/2 mv final squared. And then the change in gravitational potential energies, it goes from some height h to 0. So it has a minus h change, so minus mgh. Now on Earth, there's air friction. And because there's air friction, that it's not a closed system, and this mechanical energy is not conserved. So it has to equal to this work being done by the air. So you could see now, if you were to solve for the final velocity, the mass plays a role. And it turns out the heavier the object is, the less work has an effect. So air friction does not affect heavy objects as much as it does lighter ones, like a feather. But on the moon, because there's no air friction, so the feather and the hammer are literally not interacting with anything else, just the moon, which creates this gravitational force, thus the gravitational potential energy. The right side of the equation is 0. And what you see magically is that the mass from the two terms cancels out. So when you solve for the final velocity, it just depends on the gravitational force and the height. So the moon does have gravity. So it's not because the moon has a smaller force of gravity that makes them fall at the same time, but it's literally because there's no air. And that's what makes this term 0 and allows the masses to be canceled. So the final speed does not depend on the mass. It just depends on the initial height. And if we drop the hammer and the feather at the same height and let them go, then they will have the same final velocity and will drop at the same time. So it's kind of cool. Very counterintuitive, but that's what conservation of energy tells us, as long as there's no effect of friction. All right, a couple of more examples. So this recording is mostly about you thinking about how to apply this to various situations. Okay, here we have a skydiver. And he used to actually teach physics 7A. He was a graduate student that now is a postdoc. So suppose your physics instructor went skydiving while they're falling at constant speed. So he has reached terminal velocity. Consider the physical system to be your instructor, the atmosphere, and the Earth. So now let's think about which energies are decreasing as he is falling down. Oops, sorry, I went the wrong way. Okay, pause the video, think about it. Here's this former 7A instructor. Okay, so let's think about all of them one at a time. Kinetic energy, is it decreasing? No. He's moving down. And what else are you told? That he's falling at a constant speed. So that means that he's reached terminal velocity. Constant speed and just implies it's no longer changing. So he's just going at the same speed. So kinetic energy is neither decreasing or increasing. Gravitational energy is decreasing because he's getting closer to the ground. Thermal energy cannot be decreasing. Nothing is cooling down. There's no phase changes happening. So it cannot be more than a one above. So it's just gravitational potential energy. So same question now, but increasing. Which energy is increasing? So I didn't want to say too much in the previous one to give it away. Okay, well, we've just concluded that there's one energy that's decreasing, which is gravitational potential energy. So we know that something has to be increasing because we included everything in the physical system. In structure, atmosphere, the earth, there's nothing left. So we know kinetic energy is constant. We know this is going down. There are no phase changes happening or chemical reactions. So what's the only choice left? And that's thermal energy. So here's an example again of mechanical and thermal energy being exchanged. All that gravitational potential energy is going to thermal energy. Where's it coming from? Well, there's air friction. And that's exactly what caused the terminal velocity in the first place. So on the moon, for example, you would never be able to reach terminal velocity. Where here, that thermal energy that comes from the interaction between air and the 7A instructor, skydiving, is what's gives you this increase in thermal energy. And in DL, you're gonna do a couple of fun calculations where you will actually figure out exactly by how much does the temperature increase. And you'll actually see it's a rather small effect, because otherwise, skydivers would get super hot as they were falling through the air, which we know they don't. So you'll actually do some more numerical analysis of the situations. All right, that's it for this time. Thank you for listening. Bye.